All right, so we're going to wrap up section 13.4 with a couple more notes. And because I'm running out of time for this section, I'll do some more examples from these notes in the problem session. So suppose y is a function of x for which we cannot explicitly solve for y. So, like for example, if I had the function like y squared equals cosine of xy plus x squared or something like that. Here I have a function where I can't isolate y here, but I'm saying that y is some function of x. So this is a function of x, that's a function of x. I can't solve for y. So what we do is we still say y is some function of x. We can't figure out what it is. So what we do is we take something like this, we move everything over to the left or to the right, doesn't matter. I move everything over to the left, and I call this thing instead, once everything's moved over, I call it z equals f of xy equals 0. So once you move everything to the left, and then you name the function z or f of xy, whatever you want to call it, now you can find dy dx. So it's basically we're doing implicit differentiation. So, and that's what implicit differentiation was when we were in calculus 1. We could not solve for y explicitly, but we knew y was a function of x, and we wanted to find dy dx. Then dy dx. Now you could go through it using the calculus 1 approach and it'll work perfectly fine. Now though, if we know how to take partial derivatives, we have another way that we can go about doing this, and it's that is going to be equal to the negative of the partial of z with respect to x. So you move everything over to the left, you call that thing z, and then you take its partial with respect to x, the negative of that, and then divide it by z sub y, and that will give you dy dx. So this is just a fast way of doing implicit differentiation. And we can also do that with a function of two variables, because we said y is a function of x. So suppose we had z as a function of x and y, and we can't solve explicitly for. So, before I go on, let's see which problems in the textbook does this refer to. So for this, you will see exercises 25 through 29. All right, now if we suppose, and this part that I'm about to do is not in the reading in your textbook, so this formula is not in there, but they have some problems where you can use it. The intent of the textbook, though, is that you just do it the old-fashioned way. I'm going to show you all a faster approach. So suppose z is a function of x and y for which we cannot explicitly solve for z. So in actuality, z is some g of x, y. We just can't solve for z, but we know it's a function of x and y. Then what we do is we take the expression that we're given, that in this scenario is going to have x, y's, and z's in it. So before we had x's and y's in there, we couldn't solve for y. It would be something with x, y's, and z's in there. So say, for instance, you tack on a plus z squared and stick a z inside of there. You can't solve for z. So in that scenario, there's an analog to this, or there's some analogs to that. So you take everything, you move it over to the left, and you call that new function w equals f of x, y, z, which would be equal to 0 because you moved everything over to the left-hand side. Now, because z is a function of x and y, that means we're not going to have just, we're finding the derivative with respect to one variable. We're not going to be finding an ordinary derivative. We're going to have to find partials because z is a function of two variables. Here was an ordinary derivative because y is a function of one variable. So we're going to have a partial of z with respect to x. So the partial of z with respect to x is going to be equal to the negative of the partial of w with respect to x. So negative w sub x divided by the partial of w with respect to z. And z sub y, because remember z is a function of x and y, is going to be equal to the negative of the partial of w with respect to y divided by the partial of w with respect to z. And same thing in this scenario. You could find these by using what's called implicit partial differentiation. And in the problem session, I'll probably do a question where I do it the long way, and then you all can try it just doing it the short way. And the exercises you can look at for these are C exercises. Let's see which ones, 30 through 32. Now remember your textbook, I think there's like a project in your textbook where they ask you to come up with these formulas. These formulas right here are not given in your textbook. So if you're doing problems 30 through 32, you're welcome to use these, or you're welcome to do it the long way. Either one is fine. All right, so I'll conclude. That'll be the end of section 13.4, and then we'll start 13.5 in our next video.